好，那接下来同学在 Slack 上面发问的时候呢，如果你用中文发问，老师就用中文回复；如果你用英文发问，老师就用英文回复。好，所以如果你希望听一些中文的讲解或这个你听起来比较这个适合的说明的话呢，你就可以用中文来做发问。好，那老师可能会大概留15到20分钟左右的时间，这个来回答同学跟其他有上的问题。好，对于我们当天上课。好，那我们现在有第一位同学这个周同学他问反证法是什么？好，那好，我们陆续有同学开始问问题了但是记得我们要加分的话，就是要完整的姓名学号。好，因为这个班上老师今天这里过有同名的学生，好，班上其实有2个周叉叉，好，所以这个我们要完整的姓名学号好。好，那所以同学们如果手机在上面发问呢，接下来我们上课的过程当中，这个同学就可以这个有问题随时把你的问题 po 在 Slido 上面。好，当你听的过程中有问题，立刻就可以 po 了。好，那我们最后就会一并回答大家的问题。好，那个。好，那个刚刚在跟系主任的交流的过程当中呢，有同学问到老师还有没有在打 LOL 那感觉是系主任不知道 LOL 是什么，好，以为是微笑的意思，所以那个好，那个老师的拉克斯的专精呢，大概200多万分好，那个，然后呢，我们实验室每年学期结束的时候都会举办这个 LOW 的比赛好，实验室同学这个分组好，然后我们是有奖金的所以这个我们每年都会持续的在精进我们的这个 QWER 好，我们上次讲到1.9好，那不好意思，我们要切回英文模式咯Alright, let's give a quick review of section 1.9. We have introduced a lot of different proof strategies. For example, we have proof of existence proof, or disproof by counterexamples. So, anyone could explain in Chinese what is non-existence proof? One example. For students, you can explain in English, that's okay. You can also get the chance to have extra points. Right? Alright? Because we have existence proof, right? So once you can find a particular instance to prove something exists, then we call that constructive proofs. Okay? But for some cases, it's very difficult to discover that particular instance. So we may have other strategies, non-existent proofs. Okay, very good. And then next, what is uniqueness proof? What is 1.2? Okay. I'll say it. Okay, very good. We want to prove it exists and it will be very unique instance. Okay. So for uniqueness proof, we need to prove 2 things. Okay, first thing is the instance exists. The second thing is it exists and very unique. P is one and only one instance. Okay, so that will be uniqueness proof. And we have a very special character for unique proof. Okay, if you remember, we have exists X, right? But for uniqueness proof, we use exist X, and we have a special mark here. Okay, so next you have when you see this special character, then you will see you need to prove the uniqueness of that X. Okay, so that's a quick review of the content. Today we are going to introduce universally quantifiers assertion. Okay, so we have seen this before because for all x p of x, actually we can select one particular arbitrary instance from the domain x. Okay, so if we can prove x follow the property p of x, then we can assert for all x p of x is true because that x is randomly arbitrarily chosen from the domain. Okay, so let's see. And integer x is even, you can only x squared is even. Okay, so the complete sentence behind this example is for all x, if x is even, then x squared is even. And when x squared is even, x is also even. So this is biconditional statement. But when you see the homework assignment or other examples, you won't see the complete sentence. Because by universal quantifier assertion, you can see for any x and integer x is even, you can only express even. This implies that x is chosen from the domain and arbitrarily chosen one. Okay, so by universal quantifier assertion, we can see actually it means for all x, it follows that property. Okay, and we already know for the proof of binomial statement, we need to prove two different directions. If x is equal to true, then x squared is equal is also true. And the opposite direction, if for x squared is even is true, then x is even. Okay, so this is how we prove biconditional statement. So we just skip these two cases because we have seen a very similar example before. Okay, next for homework assignment, you will see a lot of different questions to ask you prove or disprove some progress. Okay, so let's see this example. Can we tile the standard checkerboard using dominoes? Okay, so this is the standard checkerboard. If you play this test, then we will use the black and white checkerboards, just like here. And this is what we call two dominoes, because you can see we have a square here, but usually it exists paired. Okay, so that is what we call two dominoes. And Domino's, these people were also a very famous brand of pizza. Okay, if you ask Foodpanda or Uber Eats, then Domino's Pizza also in the list of the store. Okay, and let's see this question. Can we file the standard checkerboard using Domino's? Which means we have these two domino pieces and we want to tile this checkerboard. Okay, so maybe you can put these dominoes inside this checkerboard and to see if we can tile the entire standard checkerboard using this very special two dominoes. Okay, so for this case, you need to prove or disprove. Okay, so this is one example of existence proof. Once you can see the way to tile the checkerboard using the dominoes, then we can see we can answer yes. Okay, we can do that. How we do that? Actually, you can put the two bundles in the first place of the left top corners, and then from left to right, from top to bottom, then we have two numbers, two numbers, two numbers, two numbers. And actually, you can see the standard checkerboard is 8 by 8, right? So it's even. So it's very suitable to using two numbers to fit the entire checkerboard. So by this instance, you can see once you put numbers just like here, from left to right to top to bottom, and in the end, we have the last two numbers here. Okay, so we have one possible solution here. So we completed existing proof. Yes, we can tile this checkerboard. Next, can we tile a checkerboard obtained by removing one of the four corner squares of the standard checkerboard? Okay, so which means we need to remove one of these four corners. Okay, so it looks like this. Okay, if this is standard checkerboard, once we remove one of these four corner square, okay, so you can see we have one corner empty. Okay, so that's a different checkerboard from the standard checkerboard. Can we still using two rounders to tile the entire checkerboard? Okay, the answer is no, because once we remove one square, then the total number of the grid will be odd. But we're using two numbers, it's even. Okay, so the total grid of the checkerboard should be even. Then we can use two numbers to tile the entire checkerboard. Once we remove one square, then it makes the total number odd. Okay, so we cannot use two numbers to tile the entire checkerboard. Okay, next we can extend this question if we remove the left upper and right lower squares. Okay, so if we remove this square and this square, okay, because we just mentioned that if the total number of the square is odd, then we cannot use two numbers. Here we make it even, okay, because the total number of the grid is 64. When we remove two corners of the checkerboard, the total number will be 62. Okay, it's still even. Then can we tile this checkerboard by two numbers? Maybe you can try existence proof to see we can put two numbers here, 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 and here, here. Okay. Then you can try all the ways you can think of to see if we can tile the checkerboard. Okay, then the answer is no, we cannot tile the checkerboard by two numbers. Because if you watch this checkerboard carefully, you will see this checkerboard is made of two numbers with black and white numbers. Okay. If you mark these two numbers using black and white, then you can see we have pairs of black and white for this checkerboard. But once we remove the right top corners and right lower corner, left top corner, these two corners, then you can see they all white. Okay, so if we have two white square missing, then we cannot use two numbers to tile the checkerboard. Okay, so this is one example you need to disprove this example. Okay, next let's see some open problems. Because for question 1.8 to 1.9, we have a lot of different methods to prove the question. But we still have some open problems, which means it's still open. We don't have the solution yet. And one of the most famous open problem is Fermat's last theorem. Okay, so let's see. What is Fermat's last theorem? It tells us for the equation x to the power of n plus y to the power of n equals z to the power of n has no solution in integer x, y, z when they are not zero. Okay, so we can write x times y times z does not equal zero, which means the solution of x, y, z cannot be zero. And when n is larger than 2, then we have no solution for this equation. We cannot find integers x, y, z that follows x to the power of n plus y to the power of n equals z to the power of n. And we may have one example here. Okay, if n is larger than 2, then we choose n equals 3. Then we can have x cubic plus y cubic equals z cubic. Okay, so you can replace n to other integers which is larger than 2. So you can also write x to the power of 10 plus y to the power of 10 equals z to the power of 10. So once n is larger than 2, then you can have a lot of different equations. Then the first left theorem tells us we have no solutions for x, y, z when they are integers and they are not 0. Okay. So one thing is very interesting is when this theorem or first left theorem is proposed, the author famous he says he has a very wonderful and amazing proof method to prove this theorem, but he has an A4 paper behind. Okay, but he doesn't have enough space to write the theorem. So the theorem is missing when he proposes this theorem. Okay, and then this question remains long enough over 300 years. Then nobody can solve this or prove this theorem. But now this is solved. Okay, so actually someone proved first left theorem. Okay, so we may have other interpretation of this equation. If we have one number which is the square of some numbers, for example, 25. Okay, 25 is 5 squares, right? 5 squares can be written to the sum of two number squared. For example, 25 can be written to 16 plus 9. Okay, then you can see this is 4 squared, this is 3 squared. So if n is set to 2, then we can write some square number into the sum of another square number. However, when n is larger than 2, which means we have a number which is x cubic, then we cannot write to the sum of another cubic numbers. Okay, so it follows when n is 4, 5 to any other integers. Okay, so this is the first left theorem. Next, let's see another open problem. We call this 3x plus 1 conjecture. Remember the name or keyword conjecture means it's still not proved. Okay, it still remains an open question. This conjecture, we have a transformation function t. Okay, this function t has two spatial operations. The first one is we set x to x divided by 2 if x is even, and x to x plus 3x plus 1 if x is odd. Okay, so let's see this example to see what is 3x plus 1 conjecture. Okay, just like I said, if the number is odd, then the transformation function will do the operation 3x plus 1. Okay, So if x is 13, then we use 3 times 13 plus 1, which is 40. Okay, then you can see 40 is even. Okay, then we apply another transformation function, x divided by 2. So we use 40 divided by 2, which equals 20. Then 20 is even, then we apply x divided by 2 again. So 20 divided by 2 is 10. 10 becomes 5. Then 5 is odd, so we apply 3x plus 1. 3 times 5 plus 1, which gives us 16. Then 8, 4, 2, 1. Okay? So this conjecture tells us for all positive integer x, when we apply this transformation function t, then eventually we will reach the answer 1. Okay? So no matter what this positive integers is large, small, then after we apply this transformation function, the final answer will be 1. Okay? So if you want to disprove this conjecture, one simple way is to find a counter example, right? So you can like using 1, 2, 3, 4, 5. Okay. Then to see if we can find any other counter example, the final result is not 1. Okay, but I can tell you, existence proof does not work because actually people are counting a very, very large number to 10 to the power of 13. Okay, we can still not find any counter example, but it's difficult to prove this conjecture. So we call that an open question. Okay, so this is the end of section 1.9 because we have seen a lot of different strategies when we need to prove the question. Then later on, we will see a lot of other proof methods such as mathematical induction. So we will see the for a log for on n, p of n is true, and domain consists of all positive integers. Okay, that is how we can apply mathematical induction. And then we will see also in chapter 5 structural induction. So if we want to derive some special properties about recursively defined set or recursively defined structure, then we can use structural induction. Okay. Next is one important method, which is called Cantor-back equalization. Okay, so it's a very special or very unique strategies to prove something. Okay, we will see this in chapter 2. Okay, then for the next one in chapter 6, we will not see this one, so I will leave this for you for reference. Okay, that's the end of section 1.9. All right, let's see if we have any question about this section. Hảo, 没想到有非常多的问题了哈。好，那我们看一下哈。那个作业能不能新增线上缴交的选项啊？好，那因为我们的那个作业呢是希望同学手写练习，好，那助教会以手写方式做批改，好，那如果是以线上缴交的话，里面可能会有非常多的数学公式，同学如果要用这个输入的方式，你会发现其实那个用手写方法非常多好，因为你接下来会发现会有非常多的数学公式，如果你要用电子缴交的方式的话，你势必要有一些方式把那些推荐打出来，好，会非常麻烦。那 那或者同学一直说你手写完之后拍照上传到 Force 好，那注册在改考卷的时候会比较难改哦，好，就是这个要怎么样标注同学的错误，然后让这个注标的方面都写在旁边，好，会比较困难，好，所以我们可能还是用纸本材料的方式是比较有助于同学准备作业，还有注标以后给同学做一个规划。好，老师能不能上慢一点？好，没问题。好，那我们等一下就试着上慢一点了哈。那个有时候老师会越讲越兴奋，就会越讲越快。所以如果老师讲太快的时候呢，好，同学可以稍微举个手，好，就是把老师的速度稍微放缓一下，好，那老师在我们第二章开始呢，我就尽量再讲慢一点看看。那要怎么分辨充分跟必要还有重要条件？好，那其实这个比较简单啦，就是我们说，如果 P 乘以 Q 就等于好，以 P 等于 Q， 那我们说 P 就是 Q 的充分条件 ，Q 是 P 的必要条件。好，那如果它是重要条件的话，我们就是 if and only if 的情况，好，那它就是它的重要条件了。那有同学问反证法是 condition 还是 composition？ 好，其实老师不建议同学用中文去记这个名字啊，好，那这个我们通常讲矛盾法就是 condition， 好，那反证法呢是 composition， 好，但是希望同学在修这个课的时候能够以英语的方式来这个记得我们这个在这个数学领域里面用的一些专有名词，当然你可以把它连接到中文来协助同学做理解啊。那原则上还是希望同学用那个英文来理解它的专有名词，这个是沟通方面用的，沟通上会比较方便，因为有时候你会发现有一个词它的中文翻译可能不清楚，好，所以大家讲 A 这个中文名或 B 这个中文名，在沟通上有时候就会有歧义，这个是接下来同学在那个大学课程还有研究课程都会遇到的问题哦，好，所以你会发现，我之前遇到有大陆来交换到台湾来的同学，他就说英文好奇怪，好，这个为什么你们讲话都是中英夹杂？好，比如说，他们会说那个讲话都会说，我的这个问题我要用 composition 来做证明。他会觉得为什么你要用中英夹杂的方式在沟通讲话，为什么不用中文这样？好，那实际上我们要求的就是一个精确嘛，好。好，那请问在这里问题的加分，都加分还是有第一个问题加分？好，是有加分的问题，老师就会给我加分。那老师在问问题的时候，如果没有说加分，就是一个不会加分的问题。好，那主要就是这些问题有的是简单，有些是困难，需要同学思考的。那如果老师觉得这个问题是比较有深度，需要同学思考才能答得出来的，我们通常就会列在加分的题目。好，当然从刚刚我们加分题，大家会发现，其实很多题目都是很简单就可以加到分的。好，我们来其他人有什么问题？好，unique 要怎么进行？好，就像我们刚讲的，你要先证明它是存在，好，再证明它是唯一，好，这个就是我们证明 uniqueness proof 的方式。那我们再看一下我们上课讲的题目，好。好，我们上课要跟同学证明的题目是 AR 加 B 等于0。好，这个它只有一个 unique 的 real number R 能够让这个公式成立。所以怎么证明 R 是 unique 呢？好，我们先证明 R 是存在的。存在的意思就是说，我们可以找到一个 R 让这个公式成立。好，那我们就证明了这个 solution 是存在的。然后呢，我们再证明它是唯一。好，怎么证明它是唯一呢？我们就证明，假设今天除了 R 之外，还有另外一个 solution S， 我有两个答案。好，如果我们证明它有两个答案，就不唯一了，对不对？好，所以我们实际上就假设有第二个答案叫做 S， 但是呢，我们实际上可以继续证明 R 跟 S 的答案是一样的，都是负1减 A。所以实际上，当我们假设两个答案的时候，发现这两个答案是一样的，我们就证明这个答案是唯一。好。 那这是我们证明 uniqueness proof 的方式，证明存在，再证明唯一。好。
Okay, what's the difference between non-contradictory proof and proof by contradiction? Okay, so
that's totally different strategies. Because proof by contradiction, you need to assume P in P and Q, or we want to prove the statement P, we assume not P, or not P and Q, then we derive the contradiction. So that's how we prove by contradiction. Because we assume something is wrong, then eventually you can derive something that is contradicted. Okay. So then we can make sure the assumption is not correct. That is proof by contradiction. For non-contradictory proof, maybe we can see
the previous example.
Okay. Once we want to prove some property of real numbers or rational numbers, such as x and y is irrational and x to the power of y is rational, then we can use two different cases to prove that this equation or this equation is true. But we do not discover what is x to the power of y and the corresponding x is y. Instead, we don't know this rational number, but we still can prove that this statement is true. So if we do not discover the example to prove that it exists, however, we have other strategies to prove the statement is true. So we call this non-contradictory existence. Okay. So you can see this is totally different to proof by contradiction because we didn't derive or assume something wrong and we derive the contradiction. Instead, we can have different strategies to prove the statement is true.
好，这个问题，如果 R 则 Q， 而且 Q 到 P， 好，可以传递性的推论 R 到 P， 这个推论是正确的吗？好，在原文书跟简报找不到，好，那这个应该是我们上课讲的 hypothetic syllogism， 好，好，这个一定有的，怎么会没有呢？好，好，这个 1.6。好，就是这个嘛。好，好，如果 P 到 Q 是对的 ，Q 到 R 是对的，
然后我们就可以确认 if P then R。OK。So this 这就是我们讲的传递性推论。那实际上我们在证明超元电影的时候，其实用到2次的 hypothetical solution。好，所以可以再看一下这一点，然后从超元的再确认一下这个定理。好。WLOG 如何使用？好，
那 WLOG 呢，就是好，我们再看一下这个好，我们使用的方式。好 ，without loss of generality， 好，那也就是我们在证明这个不同的 case 的情形的时候，好，其实它的证明的方式都是一样的，但是呢，我们必须反反复复的写同样的东西，只是把里面的变数给做代换。那这时候我们就可以说 without loss of generality， 好，这个在不失一般性的情况下，我们可以做这样的证明。
那我们再看一下我们上次给的例子。好，上次给的例子呢是，我们要证明 x 跟 y 好都是整数 ，x 和 y 加 y 是偶数，那 x 跟 y 也是偶数。所以我们先用矛盾法假设 x 跟 y 都不是偶数。好，当我们假设它都不是偶数的时候，实际上是有2种情形。第一种情形是 x 跟 y 会发现，当你做完这个2个 case 的证明完之后呢，这2个证明是基于你假设 X 是基础的前提下完成这2个证明的。但是你还缺了一部分的证明，是假设 Y 等于奇数的时候，你又可以写出2个 case。好，但是这个写法呢，会跟你写的这个证明完全一模一样，只是把 Y 把 X 换成 Y 而已。好，所以在这个时候呢，就是我们使用这个 keyword 的这个时机了。好，在不失一般性的情况之下，我们在假设 Y 是奇数的时候，我们也可以得到同样的证明。好，因此整个就得证了。那这个 without rules of generality 的使用的情境就是，如果它的证明方式是完全一模一样的，你只是把变数做一个代换，来证明其他的 case， 我们就可以用这句话来省掉其他一模一样的证明方式。
好，那证明数学归纳法是正确的，是透过 where order 吗？好，那这个我们就留到数学归纳法那个单元再来回答这个问题。好，那最后一个问题 ，lemma 怎么用在证明里面？好，那通常就是我们要证明一个 theorem 的时候，好，通常这个 theorem 都是蛮复杂的，所以你可能要 base 在某一些前提已经成立的情况下。但这些前提呢，可能又不是我们那么常见的。好，那这时候我们就可以用 lemma 来协助我们做证明。譬如说 lemma 1告诉我们某一个结果 ，lemma 2告诉我们另外一个结果。那从这2个 lemma 的结果，我们可以再进一步做后续的推论。所以我们就不用再证明这2个 lemma 了。但有时候我们还是会证明一下啦。好，但通常只会描述说，lemma 1我们会有一个什么样结果 ，lemma 2有什么结果，因此我们就可以从这2个结果继续往下做后续的证明的步骤。好，那这个是我们在做证明定理的时候怎么使用 lemma 的方式。当然你也可以从 lemma 开始从头做证明，但是那样整个证明就会变得又长又繁琐。好，那如果你要证明的这些事情已经是 well known 的 lemma 或是 proposition， 你就可以说，我先列出3个 lemma， 好，或是2个 proposition， 它已经告诉我们什么结果了。接下来我再 base 在这个结果之下，继续往后写我们的证明的步骤。好，那这个就是我们在做定理证明的时候使用 lemma 的方式。好，那这是同学们最后一个问题了。好，那我们这个单元就到这边。好，那我们接下来就进入第2章。好。
Okay, so chapter 2, we will introduce a lot of different basic structures, such as set, function, sequence, conditions, and matrix. Okay. You may consider this basic structure is very easy because we have learned this in high school, right? But you will see, even for master degree, when you have research in AI or computer vision, we still have a lot of definition of set, functions, even sequence or matrix for this research field. Because you can consider image is also a matrix, right? And then once you choose different matrices into a category, that will be a very special set. Okay. So although they are very basic structures, but you will see, maybe you will see these structures for your junior years, even in your master degree program.
Okay, so our first topic is about set. In this section, we will see the definition of
set and how we describe set. And most importantly, we have some important set and spatial set, empty set, universal set. And then we have the definition of subset and set equality. And then we have a very difficult sections, variety of set in 2.5. I believe this section is the most difficult one in our entire textbook. Okay, so that's looking forward for this section. And then we have the definition of hummus and content product. I believe you have learned this before, so maybe we will review this section quickly to help you remember the English name of this set.
Okay, set is one of the basic building blocks for type of objects, especially for discrete mathematics, because we have a lot of distinct objects. We are not talking about continuous functions. We are talking about the discrete properties. So set is very important to describe the properties of discrete one. Okay, and then we can apply a lot of set theory for this section, and then we can further analyze the structure of these elements. Okay, next let's see the formal definition of set. Set is an unordered collection of objects. Okay, so you just need to pay attention to the key word, unordered collection of objects. Okay, once you collect objects, which is unordered objects, into a category, then it will be a set. For example, the student. Okay, so every student in this mathematics class is a set because we don't have a specific order for each student. Okay, then we can call this object elements or members. Okay, and we use this special notation element A in the set A, we can use this notation to indicate that A is an element or a member in the set capital A. Okay, once it's not a member of the set A, we can use this notation. A is not an element of the set A. We use a notation like this. Okay, next let's see how we describe a set. Okay, the first method is called roster method. Okay, we can just list all elements inside the brackets and to indicate this set contains the following elements. We call this roster method. For example, we can list A, B, C, D, the elements of the set S. Okay, so because we are mentioning an ordered collection of objects, so A, B, C, D equals the set B, C, A, B. Because we just mentioned order is not important. So actually they are the same set as. Okay. We just need to consider the distinct elements A, B, C, D in the set. Okay. And how about A, B, C, B, C, D? Okay, so we have repeating element BC, right? It doesn't matter because we only consider distinct ordered collection of objects. Okay, so we can just ignore BC, BC because for the distinct elements, we only have A, B, C, D, 4 elements. Okay, so once you write A, B, C, D, it equals the set of the element A, B, C, D. And in this code, we use roster method because once you can list all elements in this set, then we call this method roster method. One operation we can use ellipsis to indicate the member in this set. Once the pattern is clear, for example, we can write A, B, D, and ellipsis to Z. Okay, so I believe everyone can understand the pattern because it just follows the English alphabet order A, B, C, D, E, F, G to the final alphabet Z. Okay, so once the pattern is very clear, then you can use ellipsis to describe the member or complete list of this set S. Okay, this is what we call roster method. So that's another example. When you use roster method to describe the set, we just list all elements. For example, all vowels in English alphabet, A, E, I, O, U. Okay, so we have 5 different or distinct elements in the set B. Okay, we can also list
the set of all positive integers less than 10. Okay. So positive integers are less than 10. So we have 1, 3, 5, 7, 9. We also have 5 elements in this set O. Okay, and then for all positive integers less than 100, so we can list the 1, 2, 3, 4, 2, 99 using ellipses. Okay, so this method is very easy. Once you want to use Rosen method, just give the list of these elements in the set, and that will be okay. Okay, next let's see some important set. N is the natural number. So once we collect all natural numbers into the set, we use the capital N to indicate it's the set of all natural numbers. Okay, so in this case, we also have Z for integers, Z positive for positive integers. And for real numbers, we use R, and we have R plus for positive real numbers. For complex numbers, we are using C, and we use Q for rational numbers. Okay, so please remember this important step because we will see this a lot in this section. Okay, next, another notation is what we call set builder notation. So we can collect all elements and specify its properties. For example, we can collect all x into the set of s, and we specify the property of x. X is positive integer less than 100. Okay, so that's what we describe what kind of x we want to collect into the set S. If it is positive integers and less than 100, then we will collect all such x into the set. Okay. So in this case, we use x because x is the elements. Then we use a bar here to indicate its properties. Okay, so we have a very special set builder notation using practical logic. Once P of x is true, then we collect all fx into the set of x. Okay. So we can combine the set with the practical logic we have learned in chapter 1. Okay, for rational numbers, positive rational numbers, okay, Q plus, we can still see example how to use set builder notation to define Q plus positive rational numbers. Okay, so we already know the definition of rational numbers is to rewrite this number to the form of P divided by Q for positive integers P and Q, and then Q does not equal 0. Okay, so once we define PQ using positive integers, then we can define positive rational numbers Q plus. Okay, so this is one example using set builder notation. Okay, let's look at the connection between set builder notation to roster method. Because for the roster method, we mentioned you just list all elements into the set. Okay, so if we have the set 2, 3, 4 into the set, can we write the roster method into set builder notation? Okay, so we have a lot of different ways to build the set builder notation. For example, we can write n x belongs to the natural numbers. Okay, and 1 less than x less than 5. Okay, once x is natural number and the range is 1 smaller than x smaller than 5, then x must be 2, 3, 4. Okay, so you can see this set of relation actually equals the roster method of the set 2, 3, 4. Okay, and then we can also write 2 less than x and less than and equal to 4. Okay, once we have less than and equal to, then it can be rewritten to set builder notation like this. Okay, so we can see x still equals 2, 3, and 4. Okay. Then we can also write x in real number, and this equation equals 0. Okay. So once we can collect all x in real numbers that makes this equation 0, then that will be the target set. Okay. And then you can see this equation can be further written to x minus 2 times x minus 3 times x minus 4 equals 0. So what x makes this equation 0? Actually, x equals 2, 3, and 4. Okay. Then, once you specify the properties like this, we still have the same Grosser-Messer set, 2, 3, 4. Okay. So this is how we transform from Grosser-Messer to set user.
Okay, next let's see the interval notation. We have closed interval and open interval using the square bracket. Okay, and then for open interval we use parentheses. Then you can see for closed intervals, actually x is within the range. A is less than or equal to x, and less than or equal to b. Because for the boundary conditions A and B, x follows the condition. It could be A or B. Okay, so we call this closed interval. For open intervals, actually x does not equal either A or B. So we have A less than x less than B, and then we collect such x into the set. But A and B does not in this set. Okay, so we call this open interval. Okay, next for two spatial set, universal set and empty set. I believe you have learned Venn diagram, right? Actually, we use Venn diagram to define the domain of all elements. Okay, so the universal set contains everything in this domain. We call that universal set U. Okay, and then for empty set, which means we have a set without any element in this set. So we use this symbol to indicate it's an empty set. Of course, we use this bracket to indicate the set. Once we have no elements in the set, it can be also represented as empty set. Okay, one important thing to notice is set can be an element of the other set. So actually you can put the set 1, 2, 3 into another set. Because the set contains an element A and two sets 1, 2, 3, and B, C. Okay, so set can be also an element of the other set. Of course, you can put NZQR into one set. Okay, so definitely you can see NZQR, they are set. Okay, then you can put set as an element into the other set. Okay, for empty set, okay, so you will see notation like this. We still see this is empty set. One set without anything. Okay, so actually, if we use another notation, you can see empty set we can also write as this one, right? Okay, this is also empty set, but this set does not equal a set contains an empty set. These two sets are different, right? Because this is empty set. This is the set containing the empty set. Because empty set is also a set. Okay, so they are not equal. All right, next let's see a very interesting problem. We call that Russell's paradox. Okay, so paradox means we have something with contradiction. We have some factors that with opposite properties. Okay, so maybe we can see a related paradox. Okay, Henry is a novel who shapes all people who do not shape themselves. Okay,
So which means I don't know if anyone cut your hairs by yourself. Anyone? Or you go to the salon or house store to cut your hair. Or your girlfriend cut your hair for you. Okay. So the first sentence means if for me, Professor John, if I do not cut myself for me, yes. Actually, for a while, I cut hair for myself because I want to save money when I study my PhD progress. Okay, so I have seen a lot of videos on YouTube how to cut hair for yourself. Okay, so Henry is a barber who shaves people who do not shave himself. If for me, I shave myself, then Henry will not shave for me. Henry shaves people who do not shave themselves. Okay. So based on this fact, we can have a paradox. We have a very contradictory situation. Does Henry shave himself? Okay. So we can see where this contradiction happened. Because if Henry shaved himself, then this is a contradiction. Because Henry shaved all people who do not shave themselves. Okay. So we have a contradiction here. However, what happens if Henry does not shave himself? Okay, if he does not shave himself, then he shaves all people who do not shave himself. Then Henry will shave Henry. So based on the fact that you can see, we have two situations. Both are contradictory to each other. So we call this paradox. Okay. Can anyone explain this in Chinese for me? Okay. 对对，没错，嗯，它矛盾的地方在哪里？对，OK，还有吗？另一种情形是什么？有两种情形。啊，两种情形就是 Henry 帮自己解，或 Henry 不帮自己解，我们都会得到矛盾。那如果 Henry 不帮自己解，会发生什么事？好，等下一位同学想要做一些补充，这样哈。那就帮他解。那假设他帮他解呢？他帮自己解呢？没错没错，好 ，OK。So now we can see for two cases, Henry shame himself or Henry do not shame himself. We all have contradictions in these two cases. Alright, let's go back to the original Russell's paradox. Once we have a set S, so the dimension is very unique, very special. The set S is the set of all sets which are not members of themselves. Okay, so let's see, what is the set which are not himself.
So maybe we can write something like this. Okay, if we have a set S, okay, so S is a set contains N, Q, and S. Okay, so S will be the set which is a member of himself, right? Because in this set we have S is a member of this set. Okay, so now you can see what is the set of all sets which are not a member of themselves. Okay, so if it's not a member of himself, then we collect all such sets into a set S. Then we can derive such paradox if S a member of itself. Okay. So you can follow the Barber paradox. Why we have two different contradictory cases for Russell's paradox. You can see either is a member of itself or is not a member of himself, then we derive contradictions given S is a set of all sets which are not a member of himself. Okay, I hope you can write, for example, Chinese sentence for Russell's paradox after we finish this section. Then maybe you can understand what is Russell's paradox more. 好，好，我们还剩5分钟啊，好，那我们就分析一下那个同学有没有什么问题。好，没有问题的话，我们稍微来点名一下哦。好，刚刚好像在跟那个主任交流的过程中，有同学问到今天会不会点名啊？好，好，那个刚好老师来点名认识一下同学啊，尤其刚刚还有这个校长讲的同学，好，老师更应该好好认识一下哦。好，好，那我们先看一下同学12方面的问题哦。2、3、4可以x 属于 z plus， 然后1小于 x 小于5吗？好，那它x 属于 z plus 表示 x 是正整数，然后1小于 x 小于5，所以正整数的情况下，大于1就是2，小于5就是4，中间还有一个3，好，所以这个集合完全可以写成这样的形式，没问题。好，那另外一个同学问 modus ponens 跟 modus tollens 主要用在推理跟证明吗？好，有些不懂它的用处。好，那这两个东西都是我们所谓的 rules of inference。好，就是在我们做逻辑推论的时候，这两个东西是已经被证明它们是对的了。好，所以实际上我们在做推论的过程当中，好，如果有遇到这两种情形，就可以直接说，因为它是modus ponens 或是 modus tollens， 所以我们可以直接得到什么样的结果。好，那它的用途就是我们在做逻辑相等的推论的时候，你可以直接用这些 rule， 用这些规则直接来使用，因为这些规则已经被证明它是对的了，所以这些规则都是用来做这个逻辑的推论跟逻辑证明来做使用的。好，那希望这样子有回答到同学的问题。好，那个如果同学想要看费马定理怎么解我们刚刚有放一个这个老高跟小莫的这个影片，好，在投影片里面，好，同学可以去看一下，实际上这个问题是怎么被解出来的。好，那我们接下来就来点名。好。 好，我们等一下点名的时候呢，这个因为点名的目的啊，是老师想认识各位同学啊，好，所以等一下被叫到名字的同学呢，请讲出一件令老师 impressive 的事情，让老师能够记得你。好，好，那我们要开始点名喽。好，吴玉贤没有来是不是？好，好，他是校际生哦，我不知道校际生上课的方式是应该是要来课堂上吧？好，是不是？好 ，P 是 present，好 ，L 是 late，E 是请假，A 是缺席。好，那我就直接按最后一个。好，那个等一下回答问题乱回答的就缺席喽。好，要有老师 impressive 哦，没有 impressive 记不住你就是缺席喽。好，赵浩贤真的缺席哦，还是不敢回答？邱国勋，好。OK，好，加油啊！张元照，好，好，好，所以我们刚刚跟系主任在交流的时候，有同学问什么是 fine tuning 嘛？好，fine tuning 其实就是你先修一次英文的离散，就有一个基本概念，但还没有学得很好，这时候你就可以 fine tuning 微调，再上一次中文的课，好，那就可以把你的离散数学微调得更好了。这个就是 fine tuning 最好的例子，好不好？好，林心恩，好，要缺席喽，哦。好，那个老师只玩辅助哦，好，如果你要 aggressive 一点的话，可能要找别人了哈。林浩轩，好，真的没来哦。林于晨，好，这么容易点到。张嘉欣，有在吗？好，好，有没有什么让老师 impressive 的事情？你昨天落枕，关我屁事。好，好，那个下次来我就记得你落枕了哈。林慧欣，好，好，那要加油哦，好，好，那我们今天就点到这边了，其他同学都算是有出席的，好。所以你是林医生，好，没关系，没关系，那我来修改一下。林雨晨，
对，
这个，
对，
好，那你要讲一个，
我也有打到，这样可以吗？
这样没有 impressive 吧？你的 rank 是什么？同学吗？你有 rank 吗？还是你唬烂我？
我金牌。
哦，你是金牌哦，好，那不错哦，好。助教，对，助教前面这两位，好，你有什么问题？可以找助教，好，所以怎么样？助教，跟助教合适，有什么问题？
可是我是刚刚就是那个解释。
好，跟助教加分，助教那个。 就是他帮自己解或他不帮自己解。
对啊。
所以你刚两种都讲。
那我讲。
好。
就是因为
那可能你讲太长了。没有，你刚刚其实用中文讲就好了，你还用英文来讲。
因为
就是反正都用中文的嘛。
因为我中文不知道怎么讲，就 OP。
OK。好，没问题。好。
有笔记本吗？不然我们现在是发公告，就是请你们贴个标签用的便条纸，这样，就是不要你这次的作业是写在哪几页，应该是没有。